Hello there, and welcome to the Mikey Wild Tales. I'm so glad you're here. Maybe it's been a long, busy day, or maybe you just enjoy the quiet comfort of drifting off to the universe's greatest mysteries. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, allow your mind to slow down, and let your thoughts drift. Because tonight, we're exploring a motion so vast and so constant that we don't even feel it. We're asking, why is everything in the universe spinning? You feel completely still right now, but the Earth is turning beneath you at over 1,000 miles an hour, and the entire solar system is racing through the galaxy at nearly 500,000 miles per hour. And still, we don't feel a thing. Tonight, we'll gently explore this beautiful illusion. We'll drift from the spinning atoms inside you to the great spiral galaxies, and even to the edges of black holes that twist time itself. Some facts may surprise you. Others may just stay with you as a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to leave a gentle like or subscribe. It helps others find their way here too. Now, if you're ready, take a slow breath. Let's begin our journey into the spinning heart of everything. Have you ever paused to contemplate the cosmic irony that everything in the vastness of the universe is in constant rotation, yet we perceive ourselves as entirely immobile? Our planet, Earth, is whirling at a pace exceeding 1,000 miles per hour, all while traversing an orbit around the Sun located 93 million miles away. Simultaneously, our entire solar system is hurtling through the galaxy at a velocity approaching 500,000 miles per hour. And yet, we sense absolutely nothing. Our heart's rhythm doesn't flicker. Our breathing remains steady, as though we are suspended within a universe that is furiously in motion. But what if this sensation of stillness is the ultimate deception? What if the very nature of time is merely the residue of a more profound rotation? A spin that initiated even before the formation of atoms, before the presence of light, before memory itself. This evening, we shall explore that profound riddle, asking not only why things move, but why nothing possesses the capacity to cease moving. Therefore, gently close your eyes. Permit the resonant murmur of the cosmos to pulse beneath your skin, and join me as we journey into the revolving essence of existence. If all things throughout the universe are spinning, how can we feel stuck in a moment of time? The Earth is rotating at a speed of more than 1,000 miles per hour, consistently twirling beneath your feet. Concurrently, it rushes around the Sun at nearly 67,000 miles per hour. And at this very instant, as you take a breath, the entire solar system is sailing around the Milky Way galaxy at a velocity of almost 490,000 miles per hour. Nonetheless, we are somehow oblivious to all of this movement. The liquid in your mug doesn't slosh. The air feels calm, with no perceptible drag. The stars appear to be fixed. This presents one of the greatest paradoxes of being, a contradiction between intense movement and profound peace. From the minuscule electron to the enormous clusters of galaxies, everything in the universe exhibits spin. Atoms rotate, planets revolve, galaxies spiral in magnificent formations of light and cosmic dust. Even the universe itself, based on certain cosmological models, might possess a subtle, comprehensive rotation woven into its very structure. But why, if motion is universal, do we experience such stillness? The answer begins with inertia, one of the most silent yet formidable principles in the realm of physics. Isaac Newton first articulated this principle in the 17th century. An object that is in motion will remain in motion unless an outside force acts upon it. This fundamental law is the hidden explanation for why we don't perceive the Earth's perpetual rotation. We are in motion alongside the Earth rather than in opposition to it. Your physical form, the surrounding air, the expansive oceans, the massive mountains, all these elements are turning as one, locked into a singular, imperceptible rhythm. To feel motion, a differential is required, a push, a pull, a modification. But no such modification exists here. The Earth's rotational speed is unvarying, smooth, and ancient. It is the exact same now as it was when the earliest human beings first gazed upon the constellations. Astronauts encounter this illusion on a significantly grander scale. While in orbit, they travel at 17,500 miles per hour, circling our planet every 90 minutes. Despite this, everything inside their spacecraft feels peaceful, devoid of opposition, without the friction of air. In such circumstances, motion mimics stillness. This phenomenon is designated as uniform motion. It is the identical concept that permits you to peacefully drink tea aboard an aircraft moving at 500 miles per hour. You and the airplane are moving in unison. It is only when turbulence, an abrupt alteration, disrupts this uniformity that you become aware of the motion. The Earth's movement, too, is seamless. There is no tremor, no friction, no sudden deviations. And because space is nearly a perfect vacuum, there is no sensory cue to remind us that we are spinning at cosmic velocities. Neil deGrasse Tyson once remarked, "We reside on a space rock that is orbiting a star that is orbiting a galaxy that is moving through the universe, and we call it home." It is simple to overlook this reality because our senses were never designed to operate on such immense scales. Our inner ears, which are responsible for detecting movement and maintaining equilibrium, evolved to manage walking, running, or climbing, not the rotation of a planet thousands of miles in diameter. They respond to acceleration, not to a steady, unchanging velocity. That is why you feel a car initiate movement, but not its continuous travel. On Earth, all things move synchronously with you. There is no starting or stopping, only an unending, subtle glide. Yet scientists possess the capacity to measure this concealed motion with extraordinary accuracy. The Foucault pendulum, initially demonstrated in 1851 by Léon Foucault, swings without restraint, while the ground beneath it slowly rotates. It does not require observation of the stars to validate the Earth's rotation. Its slow, hours-long pivot is the silent visualization of our planet's spin. If you have ever stood in proximity to one of these pendulums in a museum, you have witnessed the convergence of time and motion, one gentle arc at a time. On a scale that encompasses the cosmos, this rotation is anything but inconsequential. The Earth's spin dictates the cycle of day and night, stabilizes our planet's magnetic field, and provides protection from solar radiation. Without it, one side of our world would be scorched, and the other frozen solid. NASA's Goddard Space Flight Center observes that the planet's rotation has been gradually decelerating over billions of years, predominantly due to the Moon's gravitational pull, adding approximately 1.7 milliseconds to the duration of each day per century. So even within our perceived stillness, there is a transformation. Slow, imperceptible, yet absolutely genuine. When we investigate further, rotation is not just a terrestrial occurrence, it is a cosmic signature. Stars materialize from collapsing clouds of gas and dust. As these clouds contract, they spin more rapidly, an example of the conservation of angular momentum. This is the identical principle that causes a figure skater to accelerate her spin when she draws her arms inward. Every planet is a recipient of this momentum. The Earth's 24-hour rotation is a fossilized remnant of that ancient creative whirlpool. Even the sun rotates once approximately every 27 days, dragging its magnetic field through space like shimmering threads. And the Milky Way, our galactic home, completes one rotation every 230 million years, carrying hundreds of billions of stars in a vast, spiraling dance that commenced long before our planet came into being. The James Webb Space Telescope, or JWST, has captured images of galaxies so distant that their light has been traveling for over 13 billion years. And even these early primordial galaxies display evidence of rotation. Scientists from the European Space Agency, ESA, who studied these nascent formations, identified minute variances in light. One side slightly red-shifted, the other blue-shifted, a definitive signature of spin. It appears that the inherent tendency to rotate is fundamentally coded into the universe's DNA. But how can everything be in constant rotation and yet feel so still? Part of the explanation resides in relativity. According to the theories of Einstein, there is no such thing as absolute motion, only motion measured relative to something else. Therefore, from our vantage point on Earth, we are at rest, and it is the entire universe that is in motion. From a different frame of reference, the reverse is true. This symmetry is what maintains the consistency of physics, and is what renders our sensation of stillness an illusion based on perspective. In the depths of space, astronauts aboard the International Space Station orbit the Earth at nearly 5 miles per second. Yet they experience a lack of weight, not the sensation of motion. Their perception of down shifts every 90 minutes, yet their minds successfully adapt. We, too, are passengers in motion, successfully adapted to tranquility. Our perception of stillness is a mechanism for survival, a careful equilibrium between what our senses can endure and what the cosmos mandates. If we were somehow able to fully sense the Earth's movement, the gravitational pull of the sun, the drift of the galaxy, our very perception of time would fracture. This is because motion and time are fundamentally interwoven. As rotation establishes days and years, it also determines the rhythm of the cosmos. Time, as Carl Sagan once beautifully stated, is woven into the very fabric of the universe, and we are the thread. The quietude you perceive now is not the absence of motion. It is the perfect synchronicity of everything moving together. So, when you retire this evening beneath the invisible turning of the stars, remember this truth. You are not standing still. You are gently, continuously, and eternally gliding through a cosmic river. Every instant of perceived stillness is simply the universe moving too smoothly for your senses to register. And within that flawless equilibrium of motion and calm, life establishes its peaceful cadence. Take a slow, deliberate breath. You are spinning. You always have been. And the silence you perceive is the sound of all things moving together. Now, as we delve further into this narrative, let us direct our attention backward, to the moment that preceded the initiation of motion, the point when the universe itself executed its first turn. That is where our subsequent exploration commences. Part 2. Who initiated the spin of the universe? If you possessed the ability to rewind time, not merely centuries, not millennia, but all the way to the first second following the Big Bang, what would you witness? Would there be light? Would there be sound? Or would there only be an abrupt onset of motion, a swirl, a twist, the very first rotation of everything that would ever exist? The question of who or what endowed the universe with its initial spin is not a matter of philosophical conjecture, but a question rooted in physics. It is deeply embedded within the cosmological equations, within the earliest moments of time when matter, energy, and space itself began to unfurl. Astronomers refer to this period as the Planck era, a time frame so profoundly early, within 10 to the power of negative 43 seconds of the Big Bang, that our current laws of physics are unable to fully describe it. However, the scant inferences we can make suggest something truly remarkable. The universe may have been born not in silence, but in a gentle rotation. Today, scientists who are analyzing the cosmic microwave background, the faint lingering radiation from the Big Bang detected by satellites such as WMAP and the European Space Agency's Planck, have discovered minute irregularities, small fluctuations in temperature separated by mere millionths of a degree. These patterns reveal that the early universe was not perfectly uniform. Slight differences existed, and those differences subsequently expanded into everything we observe today: galaxies, stars, planets, and life itself. But certain researchers have noted an even more peculiar observation: a subtle alignment, a type of large-scale twist in how these ripples are distributed. They termed this the axis of evil, a puzzling pattern implying that the universe, at its most immense scales, might possess a preferred rotational direction. According to data from NASA's WMAP mission and subsequent observations by the ESA's Planck satellite, this alignment could signify one of two possibilities. Either it is a minor artifact resulting from measurement, or it is evidence that the entire universe once spun. If this proves to be accurate, that initial spin may have molded everything from the spiral formations of galaxies to the fundamental arrow of time. How could such a rotation originate? The crucial factor might reside in quantum fluctuations, minuscule random shifts in energy that took place when the universe was smaller than a single atom. Even within a total void, these fluctuations occur naturally. As NASA's Goddard Space Flight Center explains, quantum fields are never entirely static. They perpetually jitter. When the Big Bang occurred, those jitters were stretched and amplified by cosmic inflation, a brief yet explosive expansion that caused the universe to grow faster than the speed of light. That rapid stretching could have transformed some of those quantum jitters into swirling motions, the very first cosmic spins. Inflation theory, proposed by physicist Alan Guth in 1981, explains the universe's smooth and uniform appearance while still containing the nascent seeds of structure. However, in recent years, data from Planck and the BICEP-2 experiments has suggested that during inflation, subtle rotational modes, known as B-modes, may have existed within the primordial gravitational waves. These minute curls in the geometry of spacetime could represent the fossil record of the universe's first rotation. They indicate that the Big Bang was not just an explosion, but a twisting birth, one that imprinted spin across every scale of matter. And this conclusion is logical when we consider the subsequent events. As the universe expanded and cooled, matter began to coalesce. First quarks and gluons, then protons and neutrons, and eventually atoms. Each of these components carried minute quantities of angular momentum. When gravity later consolidated them into clouds and galaxies, that ancient angular momentum was conserved. It is the same principle that causes a figure skater to accelerate her spin by drawing her arms inward. In physics, motion does not originate from nothing. Movement must be generated by prior movement. Consequently, the first spin, no matter how tiny, had to be present from the very beginning. Astronomers today can discern the fingerprints of that rotation in galaxies far removed. In 2011, researchers from the Harvard-Smithsonian Center for Astrophysics analyzed more than 15,000 spiral galaxies and identified a subtle preference in their direction of rotation, an imbalance that might trace its origins back to the spin of the early universe. While not yet definitively conclusive, this handedness of the cosmos hints that our universe may not be entirely random after all. There might be a concealed rhythm, a silent turning that all things continue to follow. Even dark matter, the invisible scaffolding that maintains the cohesion of galaxies, could carry a spin signature. Computer simulations conducted by NASA's Jet Propulsion Laboratory demonstrate that dark matter halos twist and rotate over billions of years, guiding the visible galaxies contained within them, much like whirlpools directing leaves. Without that rotation, galaxies would disintegrate. It is as if the early universe initiated all motion, and the echoes of that movement continue to maintain the stars in perfect equilibrium. Yet, the fundamental question persists. Who or what commenced the spin? Physicists lean toward one simple explanation: symmetry breaking. In the earliest fractions of a second, the forces we now know as gravity, electromagnetism, and the nuclear forces were once unified. But as the universe cooled, they began to diverge. When that symmetry was broken, minuscule asymmetries, tiny imperfections, emerged. These imperfections, according to the European Space Agency, are what allowed structure, motion, and spin to manifest. In a universe that was perfectly balanced, no movement could occur. But in a slightly unbalanced one, it could dance. We observe this principle reflected everywhere, in the direction galaxies rotate, in the way atoms spin, and even in the manner that neutrinos exhibit a left-handed preference. Nature, it seems, is not perfectly symmetrical, and that minor flaw is what enables everything to turn. Some scientists have even attempted to ascertain whether the entire universe is currently rotating. In 2020, astrophysicist Lior Shamir from Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. He discovered that galaxies in one half of the sky tend to rotate more predominantly in a single direction than those in the other, suggesting a large-scale cosmic spin. As Shamir wrote, the universe may possess a collective pattern of motion, a preferred direction that originated in the early universe. This does not imply that the cosmos is spinning like a simple top. Rather, it might mean that the fabric of space-time itself once twisted subtly during its expansion. Even a faint twist could cascade across billions of light-years. To us, it remains undetectable, but on a universal scale, it could fundamentally shape the geometry of everything. To test these theories, NASA and the European Space Agency continue to map the universe with increasing precision. The James Webb Space Telescope is already capturing the light from galaxies that materialized a mere 300 million years after the Big Bang. Some of these ancient systems already exhibit organized rotation and spiral patterns, far too early in cosmic history to be explained by mere chance. This means that the seeds of spin were planted almost instantaneously. The universe did not have to acquire the ability to rotate. It was born turning. Even at the quantum level, spin is foundational. Every particle, electrons, protons, neutrons, possesses intrinsic spin, a built-in property of matter described by quantum mechanics. This is not the type of physical spinning we typically visualize, but a more profound mathematical rotation encoded within the wave function itself. As physicist Richard Feynman once stated, spin is one of the most profound properties of nature. It is not that the particle is literally spinning, it simply has spin as it has mass. So, in a sense, rotation was not an afterthought. It was an integral part of the blueprint of existence. When you observe the night sky, you are witnessing the legacy of that motion. Every galactic swirl, every planetary orbit, every photon of light, all are descendants of that inaugural cosmic rotation. Without it, matter would never have clumped together, stars would never have formed, and time itself would lack rhythm. Motion is not a random occurrence in the universe. It is its heartbeat. And although we may never know precisely what initiated that first spin, the evidence consistently suggests that it has always been present. Quiet, unwavering, invisible, yet inscribed into the essence of everything we can perceive. As the European Space Agency cosmologist Jan Tauber once noted, the universe carries memory not in words, but in patterns of light. And within those patterns lies the faint signature of the first motion, a twist older than time itself. So when we ask who set the universe spinning, the most candid reply might be that the universe never had to learn to move. It was born already in motion. The spin was not created. It was inherited. Take a breath. The atoms that compose your body are still turning with that initial impulse. From the smallest electron to the immense swirl of the Milky Way, the same rotation persists, unbroken for nearly 13.8 billion years. We are not separate from that motion. We are its continuation. And as we advance through this narrative, we encounter the next logical question. If rotation sculpted the birth of the universe, could it also be the reason for the existence of life itself? That is the subject of our next exploration. Part 3. Did rotation enable life? Without rotation, the Earth would be utterly silent. There would be no day, no night, no weather. Only one side perpetually frozen, and the other constantly scorched. A lifeless world, adrift in the sunlight. But precisely because it spins, this planet is capable of breathing. Every sunrise, every ocean wave, every gust of wind, all are products of the same ancient turn that began 4.5 billion years ago. The Earth's spin is not merely a movement, it is an engine, a delicate equilibrium that sustains all that we recognize as life. From the magnetic field that shields us from hazardous cosmic radiation to the temperature cycles that nourish our oceans and clouds, rotation shapes our world in ways both visible and undetectable. According to NASA's Goddard Space Flight Center, our planet's rotation speed near the equator is approximately 1,037 miles per hour, completing one full rotation every 23 hours, 56 minutes, and 4 seconds, what scientists define as a sidereal day. This unwavering rhythm dictates the pace for all biological and environmental cycles on Earth. Every plant, every animal, and every ocean current is synchronized to it, an invisible metronome ticking beneath all living things. The primary consequence of the Earth's rotation is the alternation of day and night. This motion distributes sunlight across the surface, generating temperature variations that are the driving force behind wind, currents, and weather systems. Without that daily rotation, one hemisphere would be exposed to perpetual daylight and overheat, while the other would be locked in eternal freezing darkness. The boundary separating them would be a tumultuous wall of storms, a lifeless twilight zone. But because the Earth spins, the sun rises and sets, and energy is shared consistently enough to permit stable climates and regions capable of supporting life. Rotation also influences the Earth's magnetic field, one of the most critical shields for life. Deep beneath our surface, the planet's molten iron core is in constant motion, generating a magnetic dynamo. As described by NASA's magnetospheric multiscale mission, the Earth's magnetic field is created by the movement of molten iron within its core. This field acts to deflect the solar wind, a continuous stream of charged particles emitted by the sun. Without this field, those particles would slowly strip away our atmosphere, similar to what transpired on Mars. The red planet rotates once every 24.6 hours, a period remarkably similar to Earth's. However, its smaller, cooled core ceased its molten motion long ago. Without a functional magnetic field, its atmosphere was gradually eroded by the sun's radiation, leaving behind a dry, frozen desert. Here on Earth, the magnetic field is also responsible for shaping the auroras, those gentle, glowing curtains of light near the poles. They are not merely beautiful, they are tangible evidence of our protection. Where magnetic lines intersect and interact with charged solar particles, light is created. A constant reminder that our planet's rotation still powers an invisible force field around us. But the influence of the spin extends beyond shielding and sunlight. It also governs the atmosphere itself. Because the Earth rotates, air that moves from the equator toward the poles is deflected, a phenomenon known as the Coriolis effect. This effect is responsible for the massive, spiraling systems of winds and currents that define our weather. It is why hurricanes spin, why jet streams flow, and why ocean gyres transport warm and cold water across the globe. Without the Coriolis effect, weather patterns would devolve into chaos, storms would fail to form, and climates would become imbalanced. In fact, the rotational speed of a planet directly determines its climate. NASA's Global Modeling and Assimilation Office, or GMAO, has simulated exoplanets with rotational speeds that are both slower and faster than Earth's. A slower rotation causes one side to become severely overheated and the other to freeze, while a faster rotation can generate extreme winds and shorter days that disrupt atmospheric stability. The Earth's 24-hour rhythm is nearly perfect, long enough to distribute energy effectively, yet short enough to prevent catastrophic overheating. The duration of the day also impacts biology. Living organisms have evolved internal clocks, known as circadian rhythms, that are synchronized with the planet's rotation. According to research published by the National Center for Biotechnology Information, or NCBI, every living cell on Earth possesses a molecular timekeeper that is synced to this 24-hour cycle. This rhythm regulates when plants open their leaves, when birds migrate, and even when humans sleep. If the Earth were to cease rotating, this biological harmony would be shattered. Light and dark would no longer alternate consistently, and life as we know it would be unable to adapt. Rotation also played a key role in how the Moon became our companion. Billions of years ago, an object roughly the size of Mars, named Theia, collided with the young Earth. This impact ejected debris into orbit, which later coalesced to form the Moon. The collision also dramatically increased the Earth's spin. Over the passage of time, the Moon's gravity has gradually slowed that spin, incrementally extending our days from approximately 6 hours to the current 24-hour cycle. Tidal forces between the two bodies maintain the stability of the planet's axial tilt, preventing extreme climate fluctuations. The Gaia mission confirms that this stability is essential for sustained habitability. Planets that exhibit excessive wobble frequently experience catastrophic climate variations. The Moon and Earth are now locked in a slow, gravitational embrace. The same tides that shape our oceans also cause our rotation to slow by approximately 1.7 milliseconds per century, as recorded by NASA's Jet Propulsion Laboratory. It serves as a reminder that even the length of our day, the fundamental rhythm of our world, is slowly changing, one imperceptible moment at a time. If we look beyond our own planet, we find that rotation serves a similar function in other worlds. Jupiter, for instance, rotates once every 9 hours and 56 minutes, making it the fastest rotating planet in our solar system. Its speed generates violent jet streams and storms, including the Great Red Spot, a hurricane larger than Earth that has persisted for centuries. On Jupiter, rotation creates chaos, yet simultaneously provides stability, distributing heat and shaping the planet's striking banded appearance. Conversely, Venus, which rotates backward and extremely slowly, one full rotation takes 243 Earth days, possesses almost no magnetic field. Its dense carbon dioxide atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system. The comparison is stark. Too fast, and storms become dominant. Too slow, and fundamental protection disappears. Even Mars, with a day only 40 minutes longer than ours, demonstrates the consequences when internal motion diminishes. As its core cooled, its once powerful magnetic field vanished, allowing solar radiation to strip away its air and water. Faint traces of magnetism still linger in its crust, ghostly evidence of a spin that once sustained a dynamic world. Rotation, therefore, is not an optional feature for habitability, it is fundamental. In 2023, scientists using the James Webb Space Telescope observed exoplanets like WASP-39b and TRAPPIST-1e, discovering that those with measurable spin or atmospheric circulation show clearer indications of chemical balance and temperature distribution. Without rotation, energy either remains trapped or is lost, resulting in unstable environments. As NASA's exoplanet exploration program summarizes, rotation plays a critical role in determining the climate and potential habitability of a planet. Rotation may also be linked to magnetic protection on distant worlds. A 2021 study by the Harvard-Smithsonian Center for Astrophysics noted that exoplanets with rapid spins tend to maintain molten, metallic cores for longer periods, extending the lifespan of their magnetic fields. Those fields, in turn, shield atmospheres and may increase the probability of surface liquid water, the essential element for life. So, when we ask if rotation made life possible, the data confirms it. Yes, rotation influences everything from a planet's day length to its temperature gradients, atmosphere, weather, and magnetic safety. Life, it appears, flourishes not despite motion, but because of it. Our world's rotation speed has shifted over eons, yet its effects continue to reverberate across time. It controls the rhythm of the tides, the growth cycles of forests, the migratory patterns of animals. It defines our very perception of time, not as an abstract concept, but as the physical turning of the world beneath us. As astrophysicist Neil deGrasse Tyson once stated, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Take a moment to internalize this. Listen for that turning. Every rotation carries the quiet echo of 4.5 billion years of balance and motion. If the Earth suddenly ceased spinning tomorrow, the oceans would surge toward the poles. The atmosphere would collapse into utter chaos, and the planet would lose its capacity to breathe. But tonight, as it gently rotates beneath you, everything continues to function flawlessly, quietly, seamlessly, continuously. Thus, it is perhaps not an overstatement to assert that the Earth's rotation is the silent architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, and into you. Now, as we delve even deeper into this voyage, let us track that rotation outward, to where spinning no longer simply shapes life, but begins to contort something far more strange. Because beyond a certain speed, rotation does not just cause matter to move, it can begin to twist time itself. And that is where our next chapter commences. Part 4. Can rotation distort time itself? When rotation achieves its ultimate limit, it transcends mere motion and becomes distortion. At extremely high velocities, rotating objects no longer just travel through space, they begin to exert a pull on time itself. Einstein's general theory of relativity, published in 1915, predicted that gravity and motion are intrinsically linked, two manifestations of how mass curves spacetime. The greater the energy or the spin of an object, the more it twists the geometry that surrounds it. This twisting of spacetime caused by rotation is termed frame dragging, and it represents one of the most subtle, elegant, and empirically confirmed predictions of modern physics. Imagine spacetime as a tranquil lake. When an object of significant mass rotates, like the Earth or a black hole, it agitates that lake, creating minute vortices in the very flow of time. Within these whirlpools, the direction of time itself can begin to curve. NASA physicist Francis Everett, who served as the principal investigator for the Gravity Probe B experiment, once described it this way: "As the Earth rotates, it drags spacetime around with it, much like a spinning sphere twisting the honey in which it is immersed." Gravity Probe B, launched in 2004, employed 4 ultra-precise gyroscopes orbiting 400 miles above the Earth to measure this effect. After a year of observation, NASA confirmed that our planet's rotation drags spacetime by approximately 0.000011 degrees per year. While this figure may sound negligible, it corresponds to Einstein's equations with astonishing accuracy. Even our relatively gentle planet, rotating once every 24 hours, is capable of bending the flow of time. Now, attempt to visualize a rotation that is billions of times faster and a gravitational field that is billions of times stronger. This is the condition found near a neutron star. When a massive star exhausts its fuel and dies, it collapses under its own gravity, compressing matter so intensely that protons and electrons merge into neutrons. The outcome is an object only about 12 miles wide, yet possessing a mass greater than that of our Sun. To conserve angular momentum, these stars rotate at incomprehensible speeds, up to 700 times per second. Astronomers call them pulsars because their magnetic poles emit concentrated beams of radiation that sweep across space like enormous cosmic lighthouses. As they rotate, they generate the most powerful known magnetic fields in the universe and twist spacetime so violently that even light struggles to travel in straight lines. NASA's NICER instrument aboard the International Space Station has mapped these distortions, demonstrating that time near a pulsar elapses more slowly than it does on Earth. The stronger the spin, the slower the clock ticks. Einstein's equations explain that this is not a mystical phenomenon. It is gravitational time dilation. Time proceeds more slowly in regions with stronger gravity or higher velocities. When you are near a massive, spinning body, spacetime itself is pulled into its rotation. You are unable to remain stationary. You are inexorably dragged along as if the universe itself were rotating you. This effect is particularly extreme near Kerr black holes that are rotating. Named after the mathematician Roy Kerr, who first derived solutions to Einstein's equations for a rotating black hole in 1963, a Kerr black hole is perhaps the most exotic structure we know of. Unlike a simple, non-rotating black hole, which only pulls everything inward, a Kerr black hole spins spacetime around its axis. Close to the event horizon, the speed of that rotation approaches the speed of light. Nothing, not even time, can resist being dragged along. The region situated outside the event horizon, where this frame dragging occurs, is known as the ergosphere. Within it, nothing can remain motionless relative to distant space. Every particle, every photon, is compelled to rotate with the black hole. It is as though space itself becomes a fluid, spinning in a massive, invisible whirlpool. In 2021, utilizing NASA's Chandra X-ray Observatory, scientists observed matter spiraling around a black hole situated at the core of galaxy M87, confirming that it rotates at a velocity close to the limit predicted by relativity. Inside that whirlpool, time operates in a distinctly different manner. If you could safely hover near the ergosphere, a presently impossible feat, your clock would tick slower than clocks on Earth. For every minute you experience, hours could pass for the rest of the universe. Einstein referred to this as the warping of time, a direct consequence of motion and gravity acting in concert. As he once wrote, "Time and space are modes by which we think, not conditions in which we live." The European Space Agency's Event Horizon Telescope, or EHT, captured the first ever image of a black hole's shadow in 2019, and subsequently released the image of Sagittarius A star, the supermassive black hole at the center of our galaxy, in 2022. The luminous ring we observe is not light emanating from the black hole itself, but from matter spiraling around it, light that is bent and delayed by the curvature of spacetime. Those glowing arcs are visual proof that rotation and gravity, working together, can distort not just light, but the very flow of time. The same laws apply even on smaller scales. Even satellites orbiting the Earth experience minute time differences. The Global Positioning System, or GPS, must constantly correct for both time dilation induced by gravity and by velocity. If these adjustments were omitted, GPS clocks would drift by 38 microseconds per day, sufficient to cause navigational errors of several miles. So even here, where spacetime appears calm, the bending of time is not merely theoretical. It is a feature of daily life. When astrophysicists simulate the regions near a Kerr black hole, the mathematics is stunning. Rotation can twist spacetime so severely that closed time-like curves appear, theoretical paths where a particle could, in principle, loop back to a prior point in time. Whether these loops are physically realizable remains uncertain, but they emerge naturally from Einstein's equations. In these extreme environments, the fixed meaning of past and future is lost. The James Webb Space Telescope, with its infrared sensitivity, now observes the accretion disks of distant quasars, galaxies powered by supermassive rotating black holes. JWST's spectra reveal light from these disks that is stretched and redshifted, an indication that time proceeds more slowly in those regions. Some of the light we detect today departed from those spinning behemoths over 13 billion years ago, meaning we are observing time itself stretched across the cosmos. Rotation, it turns out, does not merely shape matter. It defines how time flows in its vicinity. The faster and denser the spin, the greater the warping of spacetime. From our gentle planet to the violent cores of galaxies, the universe utilizes spin to sculpt both motion and time. What we perceive as now is different everywhere, contingent upon how quickly and how deeply the local spacetime is turning. Even light, which typically travels at the universe's ultimate speed limit, is forced to bend and slow near rotating masses. NASA's NuSTAR and XMM Newton missions have captured X-ray echoes around black holes, light briefly trapped in the rotation before finally escaping. In these echoes, time is extended like a soft thread. Measurable, predictable, yet profoundly strange. One might then contemplate whether the universe itself is twisting time on a colossal scale. Large-scale cosmic rotation could subtly influence the manner in which time flows across billions of light-years. While current cosmological data from the European Space Agency's Planck satellite does not show strong evidence for universal spin, the question remains unresolved. Even the slightest twist across cosmic distances might leave faint marks in the polarization of ancient light, hints that time itself possesses a preferred direction. As physicist Kip Thorne, a co-author of the Science for Interstellar, explained in The Warped Space-Time Near a Spinning Black Hole, the future of one observer can become the past of another. Rotation does not just bend trajectories, it bends the sequence of events, the very rhythm of existence. And yet, despite all its strangeness, the effect is consistent and quantifiable. Time dilation around rotating bodies has been confirmed by atomic clocks aboard aircraft, satellites, and in mountain laboratories. The faster you move, or the deeper you descend into a gravitational field, the slower your time elapses. This is not an illusion. It is the universe maintaining perfect balance. So yes, rotation possesses the ability to distort time. But what is even more fascinating is why that distortion appears to adhere to a pattern, a smooth, universal law that connects motion, gravity, and energy into a single continuum. From Einstein's equations to every ticking satellite, all evidence points to one truth. The universe doesn't merely move through time. It creates it through motion. Take a slow breath. Right now, your personal sense of time is intricately linked to the Earth's gentle rotation, the Sun's gravitational pull, and the galaxy's turn. You are surrounded by motion so precise that it literally dictates the seconds you live in. And if rotation is capable of bending time, what transpires when time begins to exert control over the spin? That is the mystery awaiting us in our final chapter. Part 5. If spin governs time, what governs the spin? Every second of your life is sculpted by motion, the ticking of your wristwatch, the pulse of an atomic clock, and even the rhythm of your heart. All rely on something that is spinning. Electrons rotate within atoms. The Earth turns once every 24 hours, and as it spins, it drags space-time just sufficiently to alter the way time flows. At the equator, where the Earth's surface moves fastest, approximately 1,037 miles per hour, clocks run slightly slower than those situated at the poles. This is not due to temperature or air pressure. It is due to relativity. Einstein's theory revealed that motion and gravity can either stretch or compress time, depending on your velocity and your depth within a gravitational field. So yes, spin exerts control over time, but the question persists. Who or what controls the spin? To address this, scientists examine the most reliable timekeepers humanity has ever constructed, atomic clocks. Inside them, electrons orbit atomic nuclei at defined energy levels. When these electrons transition between levels, they release photons at a precise frequency. That frequency, determined by the cesium-133 atom, defines the duration of 1 second. 9,192,631,770 cycles of radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133. These technical specifications, documented by the International Bureau of Weights and Measures, describe how every second of your life is calibrated to a tiny atomic spin. The rotation of electrons within atoms is a type of quantum spin, not a physical twirling, but an intrinsic, fundamental property of matter. In quantum mechanics, particles carry spin values that determine how they react in magnetic fields, how they chemically bond, and even how they adhere to the Pauli exclusion principle, the rule stipulating that no two electrons can occupy the exact same quantum state. Therefore, at its most fundamental scale, timekeeping is dependent on spin, not the rotation of a planet, but the intrinsic angular momentum of the atoms themselves. But just as atomic spins govern time inside our laboratories, planetary spins govern time on a cosmic level. The Earth's rotation determines the length of a day, while its orbit around the Sun dictates the length of a year. These motions are not static. They slowly drift. Tidal forces exerted by the Moon are gradually decelerating the Earth's spin, adding 1.7 milliseconds per century to each day. To maintain synchronization between atomic time and planetary time, scientists employ a system called leap seconds. Occasionally, the world's atomic clocks are adjusted by 1 second to align with the Earth's natural rotation. In a manner of speaking, we are continuously recalibrating human time to conform to the Earth's cosmic spin. If you compare clocks positioned at different latitudes, the discrepancies are measurable. A clock placed at sea level near the equator, moving fastest due to the Earth's spin, runs slightly slower than one situated high in the mountains or near the poles. This is a manifestation of both special and general relativity in action. As NASA explains, a clock on the equator ticks more slowly than one at the poles because it's moving faster and deeper in Earth's gravitational potential. The difference is minute, a few nanoseconds per day, but it is real. Your smartphone's GPS system must continuously account for this effect. Each of the 24 GPS satellites orbits the Earth at approximately 8,700 miles per hour, 12,500 miles above the surface. In orbit, they experience weaker gravity and higher speed, causing their onboard atomic clocks to run faster by about 38 microseconds per day. If left uncorrected, this would cause navigational errors of several miles to accumulate every few hours. To ensure time consistency, engineers combine Einstein's equations with real-world measurements, quite literally compensating for the curvature of spacetime induced by the Earth's rotation. Thus, every time you consult a map or receive a location signal, you are witnessing relativity in action, a silent collaboration between gravity, motion, and spin. But what initiated the spin in the first place? Astronomers trace it back to angular momentum, a quantity that is conserved in physics. When the solar system formed 4.6 billion years ago, a massive cloud of gas and dust collapsed under the influence of gravity. As it contracted, it rotated faster, just like a skater who draws her arms inward. That initial motion distributed angular momentum to every component within: the Sun, the planets, and their moons. Each body still carries a portion of that ancient rotation. No external force is perpetually maintaining their spin. They continue in motion due to inertia, the same law that ensures a planet remains in motion until something resists it. In space, where friction is virtually absent, spins can endure for billions of years. Therefore, the answer to the question of who controls the spin is no one. Once the universe was set into motion, no external influence is needed to keep it turning. However, the relationship between spin and time becomes more complex the deeper we investigate. Within atoms, spin dictates energy states. On planetary scales, spin defines the duration of days. On cosmic scales, spin drags time itself. And all these levels are unified by a single law. Angular momentum is conserved. Time, in this context, is not an independent entity. It is a reflection of how energy and spin interact. In 2016, the European Space Agency's Gaia mission mapped the precise motions of over 1 billion stars in the Milky Way. The information demonstrated that our whole galaxy completes one full rotation every 230 million years, transporting the Sun and all its planets with it in an immense spiral pathway. Every star's individual orbit adds to a magnificent celestial timekeeping mechanism. A single rotation signifies the cadence of galactic-scale time. In the same way that atomic spin establishes seconds, The spin of stars establishes eons. Even our own sun rotates once every 27 days at its equator. However, it does not spin uniformly. Its polar regions turn more slowly, a behavior identified as differential rotation. This specific twisting action produces magnetic fields, which in turn sculpt solar flares and powerful coronal mass ejections. When these magnetic disturbances arrive at Earth, they warp our planet's own magnetic field and are capable of impacting satellites and electrical power networks. Therefore, from the subatomic level to the solar level, spin is never passive. It actively sculpts fields, establishes cadences, and engages with the precise instruments we utilize to quantify time. Einstein's theory of relativity connected these observable patterns in a beautiful way. Within his equations, the very geometry of space-time is dependent upon energy and momentum, which incorporates angular momentum. To put it differently, spin actually curves time. If you were to eliminate spin, space-time would become more simple, significantly flatter, and less dynamic. Introduce spin, and it warps delicately for planets, but twists violently in the case of black holes. We could therefore propose that time itself is chronicled by motion. The second is inscribed in atomic-level spin. The day is recorded in planetary spin. The cosmic epoch is marked by galactic spin. Everything that is in motion also measures, and everything that measures is also in motion. In 2022, the James Webb Space Telescope viewed faraway galaxies whose light had journeyed for more than 13 billion years. Even within those ancient primordial galaxies, astronomers identified rotation, an indication that angular momentum was present almost instantly following the Big Bang. This implies the natural law linking spin and time has been functioning ever since the universe's first few seconds. Spin is not a consequence of time. Instead, it is part of what provides time with its forward flow. So, if spin dictates time, and spin itself emerges naturally from the principle of conserving motion, then who or what is in control of it? The most exact reply that science is able to provide is that the universe maintains control of itself. Each individual spin is counterbalanced by another. Every decelerating motion is compensated by an exchange of momentum in another location. Even the most minuscule quantum particle adheres to these exact same equations, guaranteeing that angular momentum stays perfectly conserved throughout all of space and all of time. NASA's Jet Propulsion Laboratory stated it plainly. The fundamental laws of motion do not alter. The universe operates on equilibrium. Whatever is diminished in one area is acquired in another. There is no single master clock, no concealed hand guiding it. The simple act of motion itself sustains its own temporal rhythm. Spin, therefore, is the universe's own internal gyroscope. It is its inherent method for keeping everything in alignment. From your own atoms to the stars overhead, the identical principle governs every single scale. Even as systems decay, collide, or decelerate, their angular momentum is transferred forward, ensuring the cosmic clock continues ticking. And so, when you inquire who controls the spin, the universe softly replies, "No one has to." Motion is entirely self-sustaining. It is the silent equilibrium that forms the foundation for both time and all existence. Take a deep breath. The atoms inside of you are spinning in perfect harmony with the rotating Earth, the orbiting moon, and the spiraling galaxy. You are already an integral part of that very motion. Every single heartbeat is a tiny fraction of a universal cadence that started long before there were clocks, calendars, or even light itself. Music. And as that cadence continues onward, another question gradually emerges, one that extends far beyond motion and into the very structure of the cosmos itself. If the universe is dependent on perfect equilibrium, what occurs when that symmetry is broken? That is where we will drift next. Part 6. Did the universe commence because symmetry was fractured? If everything had, at one time, been perfectly balanced, nothing at all would ever have moved. No stars, no atoms, and no time, only complete stillness. Endless and thoroughly unchanging. However, the universe we are familiar with began not with absolute perfection, but with a minuscule imperfection. A tiny fracture in that symmetry which permitted everything else to unfold. In the field of physics, symmetry signifies that the laws of nature operate in the identical manner in every direction, at every single point, and for every possible observer. When symmetry remains perfectly intact, nothing possesses a reason to undergo change. But when it breaks, even just slightly, motion manifests, structure emerges, and time acquires a distinct direction. As NASA's Goddard Space Flight Center explains it, the universe exists in the way we know it only because perfect symmetry did not endure. Let us drift back to the initial fractions of a single second just after the Big Bang. According to the standard model of particle physics, the early universe was a hot, extremely dense plasma in which the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were, for a time, unified. But as the universe underwent expansion and cooling, these forces commenced their separation. This procedure, known as spontaneous symmetry breaking, sculpted everything, from the fundamental structure of atoms to the very fabric of space-time itself. The Planck mission mapped the cosmic microwave background, the dim afterglow of the Big Bang, and discovered it was remarkably uniform, and yet not perfect. Minuscule variations in temperature, only 1 part in 100,000, disclose the initial indications of this broken symmetry. Those microscopic differences in energy density subsequently grew to become galaxies, stars, and planets. Lacking those fluctuations, the universe would have remained smooth and static, an unending, featureless fog. Even matter as we know it owes its very existence to this broken symmetry. When the universe was very young, it produced matter and antimatter in almost equal quantities. But almost is the crucial word. For every 1 billion particles of antimatter, there existed 1,000,000,001 particles of matter. That minor imbalance, known as baryon asymmetry, signified that when matter and antimatter annihilated one another, a minuscule fraction of matter endured. That remaining matter became the stars, the planets, and everything that we observe today. In 1964, physicists James Cronin and Val Fitch identified this subtle asymmetry in the behavior of particles, an effect now referred to as CP violation. Their experiment, using neutral kaons, demonstrated that the laws of physics handle matter and antimatter in a slightly different manner. This particular discovery earned them the Nobel Prize and offered the very first clue that the universe favors one direction, one specific spin, one imbalance. As ESA's particle physics division notes, without CP violation, the universe would hold no matter at all, only light. So, in a manner of speaking, imperfection is what made everything possible. The precise mechanism responsible for this imbalance is still under investigation. At CERN, the Large Hadron Collider examines particles such as the Higgs boson, which performs a critical role in shattering electroweak symmetry. When the universe cooled beneath a critical temperature, approximately 10 to the power of -12 seconds after the Big Bang, the Higgs field acquired a non-zero value throughout all of space. That particular field provides particles with mass and fractures the symmetry between light and matter. It is frequently said that the Higgs field is what froze the universe into its present form, locking in the distinctions that allowed for complexity to be possible. However, not all symmetry breaking is violent in nature. Sometimes it is gentle, similar to the way a perfectly balanced pencil will ultimately topple in one specific direction. The universe might have selected a direction for time in a comparable fashion. In the very earliest moments, time could have flowed equally in a forward or a backward direction. But a minuscule fluctuation, perhaps in entropy, perhaps in quantum probability, propelled it forward, thereby setting the arrow of time. As physicist Sean Carroll once wrote, "The arrow of time is the consequence of low entropy at the beginning of the universe, a condition of broken symmetry that all subsequent moments remember." Therefore, when we measure time, we are actually quantifying how far we have drifted away from perfect symmetry. Even the cosmic web, that immense structure of filaments linking galaxies, emerges from this very imbalance. JWST's deep field imagery reveals galaxies developing along invisible threads of dark matter which trace back to the earliest quantum fluctuations in density. Those fluctuations commenced as random variations, amplified by cosmic inflation just moments after the Big Bang occurred. What started as tiny irregularities became the fundamental architecture of the entire universe. Without this asymmetry, gravity itself could not function in the way that it does. A perfectly uniform distribution of matter would exert an equal pull in all directions, resulting in zero motion. But with a slight unevenness, gravity was able to act, pulling matter into clusters, creating galaxies, stars, and ultimately planets. NASA's WMAP mission explained it very simply. If the early universe had been perfectly smooth, no structure could have ever formed. No galaxies, no stars, and no life. Even at the quantum level, particles reveal the very same imbalance. Neutrinos, for example, are known to possess chirality. They all spin in the identical left-handed direction. This handedness of the universe might be another echo of the initial symmetry-breaking event. It is a pattern that recurs from the most minuscule scales to the most massive, from subatomic spins to galactic-scale rotations. Everywhere we look, the universe displays a clear preference. Galaxies rotate either clockwise or counterclockwise in unequal amounts. The molecules of life, such as amino acids and sugars, also have a handedness, a bias known as chirality, that is fundamental to all biology. Although life emerged billions of years after the Big Bang, its chemistry still mirrors the exact same ancient asymmetry inscribed into the fabric of the cosmos. This link between cosmic-scale imbalance and biological structure continues to fascinate scientists. A 2020 study by the Astrobiology Institute at NASA suggested that polarized ultraviolet light originating from early stars might have destroyed right-handed amino acids, allowing left-handed ones to become dominant on Earth. If this is true, then even life's molecular spin owes its specific direction to the universe's initial broken symmetry. But maybe the most elegant demonstration of this principle resides in the cosmic microwave background's polarization. The Planck satellite identified tiny swirls, B-mode polarization, that could possibly hint at primordial gravitational waves. These waves would represent the fingerprints of inflation, the universe's initial, fastest spin, and the precise moment when symmetry yielded to motion. If this is confirmed, they would constitute direct evidence that the universe's very first action was to fracture perfect balance. From the manner in which light bends to the way galaxies align, everything we are able to measure points back to that one single principle. Imperfection drives creation. Symmetry is elegant, but it is also fragile. Break it just slightly, and the universe awakens. As theoretical physicist Murray Gell-Mann once stated, if the world were perfectly symmetrical, there would be nothing. It is the deviations, the minor differences in energy, in motion, and in charge that make reality possible. When we view the universe using telescopes like the JWST, what we are actually observing is the fossil record of broken symmetry. The initial flicker of imbalance that developed into time, structure, and light. And from that minuscule imperfection, everything else followed. Galaxies, planets, oceans, and the silent, rotating world far beneath your feet. Take a slow, deep breath. You are the living proof of asymmetry. You are constructed from matter that once outnumbered its mirror twin by only 1 in 1 billion. Every single atom in your body bears the trace of that cosmic bias, preserved ever since the first microseconds of existence. So yes, the universe did begin because symmetry broke. Perfection yielded to motion, and motion in turn gave rise to time. A tiny fracture in the balance created everything that would ever spin, shine, or breathe. And as we trace that initial imbalance outward, we encounter a new puzzle. A question not concerning beginnings, but regarding what holds the cosmos together despite its ceaseless motion. Because if galaxies are spinning faster than they ought to, something invisible must be keeping them held in place. And from that very imbalance, a new mystery starts to turn. One concealed in the darkness between the galaxies. Part 7. What keeps galaxies together when they spin far too fast to exist? Galaxies rotate at impossible velocities. Stars located on their outer edges are moving so rapidly that by all known laws of physics, they should fly apart, scattered just like sparks from a spinning wheel. And yet, they do not. Something invisible is keeping them in place. A silent mass that far outweighs everything we are able to see. Astronomers refer to it as dark matter. It does not shine, reflect, or absorb light. It does not collide, melt, or form any atoms, but it does gravitate. It pulls. And that unseen pull is what prevents entire galaxies from ripping themselves apart. The mystery originated in the 1930s when the Swiss astrophysicist Fritz Zwicky studied the Coma Cluster, a vast collection of more than 1,000 galaxies drifting 320 million light-years away. Zwicky measured how rapidly the galaxies were traveling and discovered that their visible mass, the stars, gas, and dust, was not nearly sufficient to keep them bound together. The cluster should have hurled itself apart a long time ago. He proposed something truly shocking. An unseen mass had to be present, supplying the necessary missing gravity. He called it Dunkel Materie, dark matter. For several decades, his idea remained just a whisper, until the 1970s, when American astronomer Vera Rubin started measuring the rotation curves of spiral galaxies utilizing data from the Kitt Peak National Observatory in Arizona. Rubin discovered that stars far from the galactic centers were orbiting just as rapidly as those located near the core. This was a discovery that defied Newtonian physics. According to gravity by itself, orbital speeds ought to decrease as you move outward, just as planets distant from the Sun travel more slowly. But Rubin's graphs were flat. Every single star, from the center to the very edge, moved at almost the identical speed. Something invisible was providing additional gravity throughout the entire galaxy. As NASA later summarized, the rotation curves of these galaxies inform us there is much more mass present than what meets the eye. That mass, dark matter, now seems to constitute about 85% of all matter in the universe. That is roughly 5 times more than the visible matter that composes stars, planets, and people. Scientists estimate that galaxies reside inside immense dark matter halos, invisible spheres that extend far beyond their visible boundaries. Each halo functions as a scaffolding, binding the stars and gas together using gravity. Without this, galaxies such as the Milky Way would completely unravel in just a few million years. Simulations from NASA's Goddard Space Flight Center demonstrate that dark matter supplies the cosmic glue which permits galaxies to form, merge, and endure. The European Space Agency, ESA, has also long observed this invisible structure by means of gravitational lensing, which is the bending of light caused by massive objects. When light from faraway galaxies travels near a cluster that is filled with dark matter, the unseen mass warps space-time, magnifying and distorting the background light into elegant, graceful arcs. The Euclid mission, launched in 2023, is designed to map this precise effect across billions of galaxies, generating the most detailed 3D chart of dark matter ever produced. Even before Euclid, the Hubble Space Telescope provided us with stunning glimpses of this cosmic lensing phenomenon. In 2006, Hubble captured the Bullet Cluster, a location where two galaxy clusters had collided. X-ray images from NASA's Chandra Observatory revealed that the hot gas, the ordinary matter, lagged behind following the collision. But when scientists proceeded to map the total mass by using gravitational lensing, the majority of it lay ahead, distinctly separated from the visible matter. It was definitive proof that most of the mass was invisible, an independent and unseen component of the universe. Dark matter does not engage with light or electromagnetic forces, which is the reason it cannot be observed directly. It interacts solely by means of gravity and potentially the weak nuclear force. The foremost candidates are hypothetical particles like WIMPs, weakly interacting massive particles, or axions, both of which are predicted by extensions of the standard model of physics. Experiments such as Xenon-T in Italy and Lux-Zeppelin in South Dakota are attempting to detect these particles by way of rare collisions with atomic nuclei. As of now, no confirmed detection has been achieved, but the search persists quietly deep underground, shielded from incoming cosmic rays. In the meantime, NASA's Fermi Gamma Ray Space Telescope has been searching for subtle signatures of dark matter annihilation within the centers of galaxies, and the JWST has commenced observing the faint structures of galaxies in the early universe, less than 400 million years after the Big Bang. Even at that early age, galaxies already exhibited stable rotation, which suggests that dark matter halos were already established. NASA scientists wrote, "Dark matter must have formed very early, shaping the universe long before the first stars ever ignited. On cosmic scales, dark matter dictates not just how galaxies spin, but also how the entire universe evolves." Computer simulations such as NASA's Illustris and the Eagle projects demonstrate that without dark matter, galaxies would never be able to form. Matter would stay evenly distributed, incapable of clumping together under the pull of gravity. Dark matter supplied the invisible scaffolding upon which all visible matter eventually condensed. It is, as astrophysicist Neil deGrasse Tyson described it, the greatest cosmic mystery of our time, a shadow universe holding our own in its grip. Although it is invisible, dark matter leaves a trail absolutely everywhere. It sculpts galaxy clusters, influences cosmic filaments, and even impacts the manner in which the universe expands. Dark matter does not emit any radiation, but its gravity decelerates the outward expansion that started with the Big Bang. This cosmic tug-of-war between dark matter's gravitational pull and dark energy's acceleration is what defines the large-scale structure of everything. So exactly how fast are galaxies truly spinning? Let's take our Milky Way. The Sun orbits the galactic center at approximately 514,000 miles per hour, completing one rotation every 230 million years. At that velocity, and given the visible mass we can account for, our galaxy should have torn itself apart a long time ago. But the dark matter halo that surrounds it, extending perhaps 200,000 light-years beyond the visible disk, adds the necessary mass to keep it whole. This equilibrium between spin and gravity is extremely delicate. If dark matter were just slightly less abundant, galaxies would scatter. If it were slightly more, they would collapse under their own weight. ESA's Planck satellite estimates the universe's composition as 68% dark energy, 27% dark matter, and only 5% ordinary matter. So everything we are able to see, every star, planet, and person, accounts for just 1/12 of what actually exists. What makes dark matter so perplexing is that it doesn't fit neatly into our known physics. We can measure its gravitational pull, map its distribution, and simulate its effects, but we cannot yet identify what it is. Some physicists even propose that our understanding of gravity itself might require revision. Modified theories like MOND, modified Newtonian dynamics, and TVES attempt to explain galaxy rotation without dark matter. But as of now, dark matter remains the simpler, more consistent explanation. New missions are aiming to solve this enigma. ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will operate together to map billions of galaxies and measure how dark matter has shaped their growth over 13 billion years. Their objective is not only to understand dark matter, but also to reveal how it interacts, or doesn't, with dark energy, the mysterious force that is driving the universe's expansion. Even the James Webb Space Telescope contributes to this particular quest. By observing the very earliest galaxies, JWST allows scientists to test whether dark matter behaves the same way across all of cosmic time. If the formation of those early systems matches our current models, it strengthens the case that dark matter's invisible hand has always been at work. It is strange to consider that what keeps galaxies whole is something we cannot see or touch. Yet, its gravitational melody holds the entire cosmos in tune. Without it, the universe would lose its fundamental shape, its stars flung into the darkness, its clusters unbound. Dark matter is the quiet architecture of all existence, a framework made not of light, but of stability. Take a breath. Every star you have ever seen, every galaxy that drifts across your telescope, is balanced upon something invisible. You are living inside a universe held together by shadows, forces that act without being seen, guiding the motion of everything that spins. And as we trace that invisible hand through all the darkness, we begin to notice something even stranger. If dark matter holds the galaxies together, could it also have shaped the direction of life itself, even down to the spin of our molecules? Perhaps the very same hidden force that binds galaxies also left its unique fingerprint within the spirals of life, a trace we are just about to uncover. Part 8. Does the universe's spin decide the direction of life? Every living thing on Earth is twisted just slightly. Your DNA spirals toward the right. The amino acids that construct every cell in your body bend toward the left. This particular one-sidedness, referred to as chirality, is one of the deepest mysteries in all of biology. It signifies that life, down to its most minuscule molecular shape, possesses a preferred direction, a distinct bias, a spin. In chemistry, chirality means handedness. Just as your left and right hands are mirror images that cannot be perfectly aligned, certain molecules exist in two forms, one left-handed and one right-handed. In most chemical reactions, both versions are able to form equally. But in living organisms, only one hand is ever selected. DNA and RNA always twist to the right. Amino acids, which form proteins, always twist to the left. It is as if, long ago, life made a permanent decision and has followed that particular spin ever since. Scientists have spent many decades trying to comprehend why. If chemistry alone can produce both directions equally, then something outside of biology must have nudged life toward one specific side. One possible clue originates from the light of ancient stars. Light waves can be polarized, which means they oscillate more strongly in one direction than another. In the early universe, young massive stars emitted intense ultraviolet radiation that became circularly polarized as it scattered through magnetic dust clouds. According to studies conducted by NASA's Astrobiology Institute and Ames Research Center, this polarized light could selectively destroy one type of amino acid more than the other. Over millions of years, that subtle preference may have seeded the handedness of life itself. The European Space Agency's Rosetta mission added compelling evidence to this theory. When Rosetta's Philae lander touched down on Comet 67Pu, Churyumov-Gerasimenko, in 2014, it detected complex organic molecules, including amino acid precursors. Analysis of their structure showed indications of asymmetry, hinting that this chiral bias may have existed before life ever began on Earth. That implies the direction of life's molecules could have been inherited from interstellar chemistry, shaped by cosmic light and motion long before our planet even formed. Another clue comes from meteorites. In 1969, the Murchison meteorite fell in Australia. It contained more than 70 different amino acids, and scientists later discovered a slight excess of left-handed forms. As NASA's Johnson Space Center explained, the Murchison meteorite preserves chemical fingerprints from before the solar system was formed. Those fingerprints demonstrate that the universe already had a preferred molecular direction, one that life would subsequently adopt. Why left for amino acids and right for DNA? It might be more than simple coincidence. Some researchers believe the opposite orientations actually complement each other, one determining structure, the other stability. Left-handed amino acids fold proteins that can bond perfectly with right-handed nucleic acids, forming the biochemical harmony that sustains all life. Reverse that orientation, and the chemistry simply does not work as efficiently. Still, this asymmetry did not emerge randomly. It may trace all the way back to the earliest quantum imbalances, fluctuations in energy and spin that occurred within microseconds after the Big Bang. Experiments at CERN and Fermilab have confirmed that some subatomic particles, such as neutrinos, always spin in a left-handed direction. This universal handedness, or parity violation, shows that even fundamental physics is not perfectly symmetrical. In 1956, physicists Qianxiong Wu and Tsung-Dao Li proved this through their historic beta decay experiment. They demonstrated that the weak nuclear force, one of the four fundamental forces, does not treat left and right equally. As Wu herself described, nature is not as symmetrical as it appears. If even the universe's basic forces favor one spin over another, then it is not hard to imagine that life's molecules, too, inherited this cosmic preference. On Earth, this pattern continues everywhere we look. From the swirling arms of hurricanes to the spiraling growth of shells, spin and asymmetry are built into nature's very design. The Coriolis effect, caused by Earth's rotation, determines the direction of large-scale storms. Counterclockwise in the northern hemisphere, clockwise in the southern. Even our planet's magnetic field has a defined polarity, flipping occasionally, but never losing its sense of direction. The farther we look into deep space, the more this cosmic bias reappears. In 2011, astronomer Lior Shamir analyzed tens of thousands of galaxies using data from the Sloan Digital Sky Survey. He found a small but statistically significant difference in the number of galaxies rotating clockwise versus counterclockwise. That imbalance suggested a large-scale directional pattern, perhaps a relic of the universe's early, original spin. If this holds true, then the same asymmetry that governs galaxies may echo all the way down to the molecular structures of life. This connection between cosmic motion and biochemistry has fascinated scientists for many decades. A 2021 study from the Tokyo Institute of Technology simulated the effects of circularly polarized light on amino acids in an interstellar environment. They found that even a small imbalance in photon spin could lead to a measurable difference in molecular chirality. In other words, light that was shaped by cosmic rotation might have literally set the direction for life. It is easy to forget that light itself carries spin. Photons can have right-handed or left-handed polarization, a kind of angular momentum that affects how they interact with matter. When early starlight passed through magnetic fields that were twisted by rotation, that spin could imprint a bias onto the molecules it touched. Even the simplest dust grains floating between the stars might have been polarized by galactic motion, scattering light in a way that favored one molecular hand over the other. The James Webb Space Telescope is now studying complex organics in star-forming regions like the Taurus Molecular Cloud and the Orion Nebula. JWST's infrared instruments have detected prebiotic compounds, including carbon chains and nitriles, forming under the influence of polarized starlight. These observations suggest that the chemical seeds of life naturally inherit directionality from their cosmic environment. So, when we ask whether the universe's spin decided the direction of life, the evidence points toward a quiet yes. From the spin of galaxies to the handedness of neutrinos, from polarized light to chiral molecules, every scale of nature seems to prefer motion in one particular direction. It is as if life is not random at all, but rather a continuation of the universe's earliest rotation, written into every single strand of DNA. As astrophysicist Carl Sagan once said, "We are made of star stuff. Perhaps we are also made of the spin of those stars, the angular memory of their light." Take a quiet breath. Every cell located inside you still carries that same twist, a microscopic echo of the universe's turning. From the dance of galaxies to the spiral of your very DNA, the same motion continues smooth and silent across billions of years. And now, as we look deeper into that cosmic connection, another question emerges, not about beginnings, but about endings. If everything that spins must one day slow, what happens when the universe itself forgets how to turn? That is the mystery waiting quietly ahead. Part 9. Will the universe forget how to spin? Every rotation eventually slows. The Earth's days are gradually getting longer. Galaxies are drifting farther apart, their graceful spirals losing momentum. Even the stars themselves, those furnaces of motion and fusion, are burning down one by one. The universe that began with a great spin seems to be slowly unwinding. But can motion truly vanish? Or does it simply fade, spreading thinner and thinner across the very fabric of space? NASA physicist Michelle Thaler once said, "Energy doesn't disappear, it disperses. So too with spin. It doesn't stop, it diffuses. Our planet, for example, is already losing its rhythm. Each century, the moon's gravitational pull slows Earth's rotation by about 1.7 milliseconds, transferring energy outward. The result is that the moon drifts farther away by nearly 1.5 inches every single year. A gentle dance that has lasted for billions of years. Laser reflectors left on the lunar surface by the Apollo astronauts confirm this drift with millimeter precision. If this process continues, Earth's rotation will one day lock with the moon's orbit, each one always showing the same face to the other, just as the moon already does to us. It will mark the end of tides as we know them, the end of the daily cycle of ocean and air. Planetary spin, once so vibrant, will fade away into equilibrium. Elsewhere in the solar system, the same story plays out. Mercury is already trapped in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the Sun. Venus, with its incredibly dense atmosphere, has slowed to an almost unearthly crawl, 1 rotation every 243 Earth days, and in the opposite direction of its orbit. Even Mars, whose day is only slightly longer than ours, is gradually losing speed. Over cosmic timescales, spin is not forever. It is a rhythm that is winding down. The slowing continues beyond planets and into the heart of galaxies. Using the Hubble Space Telescope and the Very Large Telescope, VLT, astronomers have measured the rotation of spiral galaxies billions of light-years away. When compared with modern galaxies, those ancient systems appear to have spun faster, with tighter arms, denser cores, and more angular momentum. As time passes, gravitational interactions and cosmic expansion gradually sap that motion away. According to a 2020 study from the Leibniz Institute for Astrophysics Potsdam, galaxies may lose a portion of their spin through collisions and merges. When 2 galaxies merge, their stars do not crash into each other, but their dark matter halos interact, redistributing angular momentum outward. This process leaves the galaxies rounder, slower, and more diffuse, the spiral giving way to the ellipse. The European Space Agency's Gaia mission has mapped over 1.8 billion stars in the Milky Way, revealing that even our own galaxy is evolving toward stillness. Its outer arms, once tightly wound, are gradually stretching. Over billions of years, friction with dark matter and nearby galaxies will drain its spin, softening its spiral form. Eventually, the Milky Way and Andromeda will collide, not in chaos, but in a slow, silent fusion. Their combined rotation will settle into a single, massive, nearly motionless elliptical galaxy. But spin doesn't vanish when the stars fade. It transforms. When a massive star dies, it collapses inward, conserving angular momentum and spinning faster than ever before. This creates neutron stars, city-sized objects that can rotate hundreds of times every second. NASA's NICER instrument on the International Space Station has observed pulsars spinning 716 times per second, their beams sweeping through space with the precision of atomic clocks. Yet even these cosmic lighthouses eventually slow down, radiating away energy as gravitational waves and magnetic fields. As time expands even further, rotation becomes scarce. Stars fade. Black holes, the last great engines of spin, slowly evaporate through Hawking radiation. In 1974, Stephen Hawking predicted that even black holes are not eternal. They leak energy and lose their angular momentum over unimaginable timescales. A spinning black hole, known as a Kerr black hole, gradually transfers its rotation to the surrounding space, leaving faint ripples of energy that stretch across the universe. The LISA mission, planned for the 2030s, will detect these gravitational whispers, waves caused by spinning black holes merging and fading. Each detection will be a record of rotation being released into space-time, echoing across billions of light-years. Even when the black holes themselves are gone, their rotational memory will remain imprinted in the geometry of the universe. So, will the universe ever truly stop spinning? Not completely. Angular momentum cannot be destroyed, only spread thinner, shared among an ever-expanding sea of particles. As NASA explains, in an isolated system, angular momentum is always conserved. The universe, in this sense, never stops moving. It only redistributes its motion. Still, there may come an age when motion becomes imperceptible. In the far distant future, long after the last stars have died and galaxies have faded, the universe will enter what physicists call the heat death. Energy will be perfectly, evenly distributed. There will be no temperature gradients, no flow, no reason for anything to move. Rotation will persist mathematically, but without contrast or structure, it will have no meaning. Some cosmologists, including Lawrence Krauss and Brian Greene, describe this as the cosmic silence, the final calm after every vibration, every orbit, every single spin. In that distant epoch, protons themselves may decay, and black holes may fade into bursts of radiation. Only faint background photons and neutrinos will drift endlessly through space, carrying the last traces of the universe's once grand rotation. The James Webb Space Telescope peers deep into the past, but it also reminds us of the universe's eventual future. Every ancient galaxy it observes is another tick backward on the cosmic clock, showing us how rotation once defined all structure. In its images, we see both beginnings and endings, motion kindled by imbalance, and motion fading into stillness. Even so, spin leaves fingerprints that cannot be erased. From the polarization of the cosmic microwave background to the curvature of spacetime around dying stars, the memory of motion remains encoded in the universe's design. It is not movement that we lose, only the strength to notice it. Take a long, slow breath. Right now, the Earth's core still turns. The stars still orbit, and the Milky Way still drifts through the darkness. Every motion you know is a flicker of that ancient rotation, one that will outlast you, but will not outlast eternity. And when that eternity finally arrives, when the last spin finally stretches into absolute silence, something else will still remain. Not movement, but the memory of movement. Because even when the universe forgets how to turn, its geometry will still remember that it once did. As we approach that horizon of stillness, another question quietly unfolds. If every atom, every planet, every galaxy is slowing down, what does that make us? The one still moving within it. That is where our next story begins. With motion not of the cosmos, but of consciousness itself. Part 10. Are we the universe remembering its own motion? Every atom inside of you is spinning. The electrons orbiting your nuclei, the protons and neutrons inside them, the quarks deep within, all are caught in ceaseless motion. That motion is not random. It is a continuation. The faint, persistent echo of the universe's first rotation. When you move, when you breathe, when your heart beats, you are not separate from the cosmos. You are part of its oldest memory, motion itself. In physics, angular momentum is the persistence of spin, the fundamental rule that keeps motion alive. It is why galaxies still turn, why planets still orbit, and why atoms still vibrate after 13.8 billion years. According to NASA's Goddard Space Flight Center, angular momentum cannot be destroyed, only transferred or shared. That means every spin in the universe, from the grandest to the smallest, is a continuation of the same original rotation that began at the Big Bang. In the beginning, the universe was not still. Measurements from ESA's Planck satellite show that the cosmic microwave background, the faint afterglow of the Big Bang, carries subtle anisotropies, slight directional differences in temperature. Some cosmologists interpret these as traces of the universe's first angular momentum, the original twist that set everything in motion. That primordial spin never vanished. It fragmented, spreading across all scales, from galaxies down to atoms. When stars form, clouds of hydrogen and helium collapse under gravity. As they shrink, they rotate faster, conserving angular momentum just like an ice skater pulling in her arms. This same rule gives rise to accretion disks around young stars, planetary systems, and even black holes. Each planet, each moon, carries a fragment of that spin embedded in its orbit. And within those planets, inside every rock, ocean, and living cell, the pattern continues at smaller scales. Our atoms, too, hold rotational memory. The electrons that define chemical bonds obey the quantum property of spin, a fundamental angular momentum intrinsic to all particles. This spin isn't literal spinning, but a quantum state, a value that determines how particles interact with magnetic fields. Without it, chemistry would not be able to exist. NASA's Quantum Laboratory Initiative describes spin as the engine of atomic structure, the difference between chaos and stability. In this sense, you could say every piece of matter carries an ancient choreography. The spin of particles leads to magnetic fields, which lead to structure, which leads to stars and planets, and ultimately to life. Your neurons fire using electrical potentials shaped by these very same fields. Every thought that crosses your mind is an alignment of charged particles, a kind of ordered motion. So when we ask whether consciousness might be the universe remembering its motion, the question is not poetic. It is physical. Each brain wave, each signal is built upon rotations that have existed since the dawn of time. The magnetic fields generated by your neurons are faint echoes of the same electromagnetic principles that guide pulsars and magnetars. As astrophysicist Neil deGrasse Tyson once said, "We are not in the universe, we are part of the universe, and the universe is in us." From a scientific viewpoint, memory is a form of pattern preservation, information encoded in physical states. Atoms remember through spin orientation. Cells remember through molecular structure. Stars remember through rotation curves, and the universe remembers through the geometry of space-time itself. Einstein's general relativity teaches us that energy and momentum shape space-time's curvature. Every movement, every rotation leaves a small indentation, a swirl in the geometry of reality. This is known as frame dragging, confirmed by NASA's Gravity Probe B experiment in 2011. The probe measured how Earth's rotation subtly twists the surrounding space-time, like a spoon stirring honey. It proved that spin is not confined to objects. It extends into the very fabric of the cosmos. In a similar way, even your movements, though infinitesimal, also disturb space-time, ever so slightly. The difference is just one of scale. Your body's atoms spin billions of times per second, generating magnetic interactions measurable by quantum sensors. Each micro-rotation contributes to the ongoing record of motion that began long before humanity ever existed. If all motion leaves traces in space-time, then perhaps what we call awareness is the way the universe perceives those traces through us, not as emotion or spirit, but as physical continuity, matter recognizing its own persistence. Consciousness, in this purely scientific sense, is a system's capacity to reflect its internal state. And that reflection is written in movement. Even light, the messenger of the cosmos, carries angular momentum. Photons possess spin 1, which determines how they polarize and interact with matter. Polarization patterns across the cosmic microwave background act as the oldest record of rotational memory in existence. ESA's Planck satellite and NASA's WMAP mission mapped these swirls in exquisite detail, showing faint B-mode patterns, signatures of primordial gravitational waves rippling from the universe's first motion. So when you gaze at starlight, you are literally seeing the memory of spin, light that has been twisted and stretched by billions of years of motion. And that light enters your eyes, triggers chemical reactions, and becomes part of your own neural motion. In that way, the universe does not just remember its spin, it continues to experience it through every observer it creates. Even as the cosmos expands and cools, these traces persist. Galaxies may slow, but their angular momentum never disappears. It is passed to intergalactic gas, to dark matter halos, to radiation. The JWST has detected faint filaments of gas stretching between ancient galaxies, structures shaped by those very transfers of spin. Every wisp of matter still moves to the rhythm set 13.8 billion years ago. And when the last stars fade and motion becomes silence, those patterns encoded in gravitational waves, particle spin, and frozen light will still ripple faintly through empty space. They are not gone. They are written into the shape of everything that remains. Like fossils of rotation, they form the universe's deepest kind of memory, motion preserved as geometry. Carl Sagan once reflected, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the language of physics, that knowing is not mystical. It is through motion, energy, and spin. The universe continuously encodes and retrieves its own history. Take a breath, slowly. Every atom inside you continues to turn, the same spin that once ignited the first stars. You are a moving archive, a living part of the universe's ongoing memory. And as we follow that idea, that motion may be the cosmos remembering itself. A new horizon opens. Because if memory is movement, then perhaps what we call life is the brief moment when the universe pauses, just long enough to notice it is still spinning. That, dear listener, is where our next chapter quietly begins. If this quiet journey has brought you even a small moment of peace, I am deeply grateful you have spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It is what keeps me creating these cosmic lullabies for wandering minds like yours. And if you are kind enough, please tell me in the comments where you are tonight and what time it is where you are listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence. They are like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe turn softly around you.